Okay, welcome back. So we were discussing this example of local versus global stability. So what I mean is this. So we always say when there is more than one steady state, we cannot talk about global stability. So I'm explaining why is this the case. All right, why this is the case. So if we have more than one steady state, so let me rewind for a little bit. So stability question is about deviating from the steady state. All right, so let me use a clear figure. So stability question is this. So I have this two variable system, let's say, all right, and there's this let's say steady state. All right, so let me so this will be nonlinear. Okay, so there's the steady state, right? Let's say this is y, this is x, and we can have anything really, right? So we can have, for instance, a spiral, right? So this looks like a spiral. Now, when we talk about stability, we move away from the steady state first, all right? So if steady state is here, okay, so this is the steady state, x star, y star. So first, to talk about stability, first we have to move away from it. Let's say to a point like this, all right? Let's say to the point x prime, y prime. Then we ask, okay, what happens in time whether I go back to the steady state, all right? So this is the stability of this steady state, all right? When I ask whether I go back to it, I'm basically talking about the stability of this steady state. Now, if there is only one steady state, then I can talk about two different types of stability. One is global, one is local. In the global case, I basically take this deviation to anywhere, all right? Remember the definition of the stability. So it requires the deviation here, I mean, there we denote it by x0, okay? So we should talk about any x0, y0 that is in R square, okay? So that deviation could be anywhere. Or if I want to be more specific about the local dynamics, I can linearize the model, right? As before, I can linearize the model. When the model is linearized, now what I find is true only around the steady state, okay? Only around the steady state. Now, this becomes a local stability analysis, all right? So what is the trade-off here? Well, trade-off here is this. So here in the local analysis, I'm much more accurate, but I don't know what happens when I am here, okay? I don't know what happens when I am here, because if I move away from the steady state, this linearization is not very accurate, okay? You see the difference? You see? This linearization is not very accurate if I move away from the steady state, okay? So the trade-off is there. Now, if we have two steady states, okay? If we have two steady states, this is again xt, this is yt, this is suppose that yy, this is xx, then I cannot talk about global stability here, right? Because I do not know in general whether this point or this point or this point or this is in the basin of attraction of this steady state or this steady state. Okay, because it is about deviation, right? Initially, I have to deviate from the steady state whose stability I am working on. All right, I have to deviate. Since this deviation could move me to a point where the equilibrium is now moving to the other steady state. Okay, this is the reason I cannot talk about global stability when the set of steady states has more than two elements, more than or equal to two elements. Okay, so that was the idea. In some models, for instance, you can check some papers by Lagerlöf on state capacity. Okay, in some models there are different. So let's say you have two variables again, but there is a boundary. Let's say so before that your system moves like this. Let's say, okay, but beyond that constraint, your system moves like that. Okay, then again you have two steady states. Okay, but they have completely different dynamics. Okay, that could be I mean, there could be many different dynamics in such models. Okay, so sometimes the behavior of the system changes qualitatively. Okay, so that was the notion. So local stability is an entirely different concept than global stability. All right. Was that clarifying enough? Was that good enough?
Yes, thank you.
Okay, so now I want you to give a sufficient condition for global stability. So obviously, we want to have this n-dimensional system. So xt is in Rn, and phi is a vector valued function. Okay, and we assume that there is a steady state. Okay, so there exists x star such that this is true. Then the sufficient condition is this: phi is a contraction mapping. Now you're gonna ask me what a contraction mapping is. A contraction mapping satisfies this property. So I want you to imagine two vectors, okay, 2 points in Rn. Okay, xy in Rn. So if phi is a contraction mapping, for all x and y in Rn, we have this property. The distance between phi x and phi y will be less than beta times the distance between x and y for some beta between 0 and 1. Okay, so if this is true for all vectors, okay, phi is a contraction mapping, and then that x star is global stable because there's nowhere to go. Do you understand? So how do we understand that? This basically tells you that you take any 2 points, right? Any 2 points in your so this is like And of course, so let me maybe I can do this notation. So notation here is a bit problematic. Maybe I can say this. Okay, so I have two different points, XA and XB. Okay. So the distance between these 2 points, so this is your x1t, this is your x2t, let's say, okay, and this is xa, and this is xb, right? So when I say xa, I mean xa1 in this example, and xa2. When I say xb, I have xb1 and xb2, right? So I take these 2 points, the distance between these 2 points time a factor of beta that is between 0 and 1 will be greater than the distance between x t plus 1a x t plus 1b, okay? So basically in time, there is a contraction between the distance between two different xt1 levels, okay? So in time, there is always a contracting distance between these x's. So if that's true, then that x star will be globally stable. So this is a sufficient condition. It is a very stringent condition, which may sometimes not satisfy. Okay, it is not satisfied at all times. Sorry. Okay, but this is given, and in the when we discuss dynamic programming, I will explain in more detail. So because we're going to use a contraction mapping theorem there as well, as in here, for a slightly different purpose though. When we discuss Bellman equations, you're gonna see. So we're gonna revisit this concept again. Okay.
XA and XB is neighborhood, the X star, or what
No,
is the difference
no,
between
it's
X
not.
star?
No, it's not related with that. Here we are taking any 2 points in the domain of this function. All right. So this is a vector valued function, right? So we take any 2 points. You should be careful here with the dimension. When I write this, we have, let's say, x1t plus 1 phi 1 x1t x2t, let's say if n is 2, right? Then x2t plus 1 phi 2 x1t x2t. Okay, so when I write xa, I basically mean a vector in R2. When I write xb, I mean a vector in R2. Okay, so the contraction mapping property tells me that the so if you have, let me rewrite this differently. So if you have the distance, remember the formula for the distance. If you have 2 vectors, the distance is so x a1 minus x b1 square x a2 x b2 square. So that's the distance. Now that distance between xa and xb multiplied by a number that is between 0 and 1 must be greater than the distance between the points x1t and x2t that will move to. All right. So in time, when t passes from t plus 1 to when t passes to t plus 1, that distance contracts. That distance gets smaller.
Okay, I see.
So it is like a limit concept. All right. But this must be true. This must be true. That's important. This must be true for all XA and XB in Rn. Okay. If it is true for any XA and XB, then it is always converging to X star. Okay. Any XT converges to X star. That's the idea. That's global stability. Okay, because this property, contraction mapping property, will be true for all XA and XB, for any two vectors. Okay.
Okay, thank you.
So, of course, most of the time, we want to be interested in the local analysis of the steady state, right? So we linearization. Okay, so again, we will have a linearized version of this, right? So this is my original nonlinear model. And then I'm going to apply Taylor approximation and arrive at this system. So this is m by 1. This is m by 1, right? So this is m by 1. This will be n by n, m by 1, n by 1. Okay, this will be a vector, and this will be a matrix. So this matrix will be called the Jacobian of phi. Okay, it will be the matrix of first order derivatives. Okay, so what do I have? Once again, I start with a steady state. Okay, so there exists an X star such that it is a steady state. Then I will write a first order Taylor approximation. So how do I do that? Remember, for any function, let me open a box here. So this is just a refresher. Okay, this is just a refresher. So if you have a function f of x, okay, and you can take any point, such as point 0, okay, x0, and you can approximate this function in this way. So you take the first derivative, evaluate it at x0, then you look at the deviation of x from x0. Then you take the second order derivative, okay, again evaluate it at x0 divided by 2 factorial. Then look at this, okay, that goes on, right? Now here we're gonna use a first order approximation around the steady state, okay? First order approximation around the steady state. And be careful, we have n different functions, right? We have phi 1x, phi 2x, phi nx, okay? This is just what we're gonna do. So the idea is, of course, this. So I want to approximate x1t plus 1, right? So first, and I want to do that approximation around the steady state. So first, I do this. Then I take the first order derivative of phi 1 and evaluate that derivative at the steady state. And this is with respect to x1t, all right? Then I multiply it by x1t minus, careful here, x1 star. Okay, because when I write x star again means x1 star, x2 star, dot, 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 xn star. Okay, so for the first argument, I do this. For the second argument, I again look at the phi1 function because this is what I approximate, right? I'm still at the first one. Now I take the derivative with respect to second argument, evaluate it again at the steady state. Then I look at this. Okay, now that goes on until I arrive at the last derivative. Again, the derivative of phi1 with respect to xnt evaluated at the steady state and xnt minus xn star. Okay, so that's for the first one, right? Now for the second one, what do I change? I change these elements. For the second one, okay, for the second one, I have x2t plus 1, and these are going to be seconds. Okay, these are going to be seconds. In the third one, I'm going to use the third function. Okay, the logic is the same because I am using first order Taylor approximation around the steady state. Okay, so in general, this is the formula. In general, we have x, so maybe I can use a new page. So I have xit plus 1 equals phi I x star summation from j to n, right? The derivative of I, careful, evaluated at x star. This derivative is with respect to xjt times xjt minus xj star. Okay, now be careful with i's and j's, but that's the general formula, right? By the way, this is the same as the continuous time model. Almost the same idea, first order Taylor approximation. Okay, and of course we don't care about the residual term because there's always a residual term there, but we don't care about that. Okay, so if you do that, you realize one thing. So this is your now Jacobian, this A matrix, right? This is the matrix of first derivatives. So you have phi1 x star x1t, phi1 x star x2t dot dot dot, phi1 x star xnt. Okay, then you have phi2 x star x1t, phi2 x star x2t dot dot dot, phi2, sorry, phi2 x star xnt, and that goes on until you arrive at phi n x1t, phi n again evaluated at x star with respect to x2t dot dot dot, and finally you have function phi n, the last one, evaluated for, so the derivative is with respect to xdn. Okay, oops. So this is your Jacobian matrix, right? And then you have B. What is in B? Well, in B you have phi 1x star minus summation, that derivative, right? That derivative times x j star from j equal 1 to n. Then you have phi 2x star minus, again, this, again, the derivatives, xj star. So this is again from j1 to n. Okay, this is phi 1, this is phi 2, right? That goes on. So at the end, therefore, you have your linear system. Okay, and if you have this linear system, how do you define the steady state? Well, you have x star, ax star plus b, right? So this could be written in this way: ix star equals ax star plus b. So you have ix star minus ax star equals b. So you have I minus ax star equals b. Now, what is I, by the way? I is n-dimensional identity matrix. Right? It is n-dimensional identity matrix. Okay? Then from this, if there is the inverse, you multiply it from left, of course. You have to multiply it from the left. You have the inverse, then this is itself the identity matrix. So you have ix star equals this. So you have steady state, which is equal to that. Okay. If the inverse of a matrix exists, so this is a general property of, so this is a general result in linear algebra. So if the inverse of a matrix exists, then that inverse is unique. Okay, and that existence requires the determinant of the matrix to be different than 0. Okay, so we require that. If that's true, then this linearized system will also have a steady state. Okay, and that steady state will be there. All right, and it will be, of course, you should be realizing that it will be the same thing. Okay. Now, from this point on, I'm gonna give you some results on the types of equilibrium. All right, because once again, we're gonna look at the eigenvalues of A. Okay, for an n-dimensional system, we will typically have eigenvalues, lambdas, and the magnitude and the sign and the magnitude will tell me whether the steady state is stable, whether the convergence or divergence is oscillatory or non-oscillatory, and we're gonna study these things. Okay, let me give you one final example exercise for you to work for linearization. Okay. Then next week we start with those examples. There will be many different types of examples that we're going to discuss. So this is just an example. So you have this system xt plus 1 equals xt times yt to the theta minus beta. Here theta t is between 0 and 1, beta is greater than 0. And you have yt plus 1 equals yt divided by xt minus gamma, and gamma is positive. So I want you to find the set of steady states, okay? XY pairs satisfying xt plus 1 equals xt and yt plus 1 equals yt. Then I want you to linearize the model, linearize the system to arrive at something like this. Okay. So basically, you're going to find A and B. Okay. So this is your exercise. It's a very simple exercise, actually. Next week, we're going to continue from this point on. And possibly, we're going to finalize our discussion of discrete time dynamical systems with more examples and more stuff. Then 2 weeks later, we're going to start discussing dynamic programming. Now we have 4 minutes if you have quick questions, or we can reconnect again and discuss if you have if I leave many parts unclear. So the idea of linearization is the same. So once you get the I mean, just handle with it. I mean, it's not difficult. So you are just taking derivatives and evaluating those derivatives at the steady state. Okay, so you can find some other problems in my website just to make some practice as well. And the idea of contraction mapping. Think about this. Think about the distance. How that distance can contract. So that's the sufficient condition for global stability. Anything? All right then. So next week, yeah, you may want to take a quick look at Galore's textbook. I think the stuff I am going to show you is at chapter 3. Either chapter 3 or chapter 4. I don't remember. Either chapter 3 or chapter 4. Just take a quick look if you find it useful. But it's better if you focus on the lectures. Okay then. I will see you next week. I'm now ending this session now.
Thank you.
All right. Bye-bye. Bye-bye.